Well, good afternoon, everyone. This is John Wazinski. I'm the Technology Director here at America Makes, so I'm going to act as the moderator for the discussion today. I'd like to welcome everyone to the webinar series for today, and I guess the beginning of 2019. We're going to be hearing from Jay from MELD, and he's going to talk to you about a really interesting technology and spend, a good bit of time talking through that. Just a couple of reminders for everyone as we get started. Be aware that your audio is not turned on, anyone except myself and Jay. So if you have questions, please put them in the Q&A box that's on the right-hand side of your screen. We encourage you to ask questions, so anytime throughout the course of the presentation, go ahead and type questions in there. We'll be keeping track of those, and then we'll ask them at the end of the briefing. Anything that he did not cover, we'll make sure they get addressed. So with that, I will welcome Jay to get going. Thanks.
All right. Thank you, John, and thank you all for attending the America Makes webinar series. And today it's all about MELD, solid-state metal AM technology. I encourage you, I'm sure this presentation goes up into some type of a YouTube format. You see my contact information there. If you want to reach out afterwards to discuss some specifics, that's great. Otherwise, I'll address questions towards the end. I'd like to start off with a different way to start off the pitch. MELD has been developing the technology for 10 years. We've been working with beta customers for 4 to 5 years. We've been selling machines a little over 2 years, at least began to launch our commercial machine about 2 years ago with University of Alabama being our first customer. And we came out as a new company, MELD Manufacturing. We were previously branded as Additive Friction Stir. And of course, we wanted to create our own vocabulary, so you have to say the word MELD. So that's the story behind MELD. And we're a small business, woman-owned. And what I like to do is just say we came out in April, and within a week, we were awarded the AM Innovator of the Year award at the Rapid Show down in Fort Worth, Texas. We were awarded a golden award from R&D 100 called the Market Disruptor, and as well as an R&D 100 winner. The Automobile Association has given us an award through SAE TechBrief. And, my point is there's lots of additive manufacturing technologies popping up, kind of like the whack-a-mole fair game, if you ever played that before. And you don't know which to spend time on, which to invest in, which to spend some resources towards evaluating technology. So I just start off with saying, in less than 10 months, for all these awards to migrate over to MELD, our technology may be interesting, and my goal here is to present the technology so you'll agree that it is interesting. What do? We sell off-the-shelf standard machines, and then working with the beta customers for a few years, we migrate to special purpose machines for large size applications. We obviously do R&D development work as well as some service bureau type component development and manufacturing work in order to demonstrate our technology. And with that in mind, you'll see the list of our patents. We have 13 patents to date with other patents pending and other patents getting ready to be submitted. And I'm going to start with awkwardly flipping over to my browser to show you a video that shows the process. You can see the MELD tool spinning at high RPMs. We monitor two main variables. It's, RPM or torque speeds, and then with a ball screw or with a linear force. And we deposit any metal type. And I'll get more into the mechanics. But here you see us printing aluminum 6061. The Z-axis height, they're about 1 millimeter each. We're a high-speed deposition process. We've achieved with aluminum up to 30 pounds an hour. That's pretty darn fast. Doesn't mean every application is 30 pounds an hour, but that basically assumes a 2-inch wide track. So right there you see you just saw a video, let me get that out of the way now, sorry, of a project where we just recently printed a 285-pound cylinder. That's as much as I can go into at this stage. but it has obviously an end-use application, and we were permitted to show that little video there. And now to get back to my presentation. So MELD, it's a solid-state metal AM technology. It's an emerging disruptive process because we extend the applications of friction stir welding, and now we transition to an additive manufacturing repair and previously unjoinable configurations by enabling the ability to add metal in situ to the process. So we have a friction stir welder has a solid tool with a solid nub. Ours is similar, except we have a hollow, where's my mouse? We have a hollow cylinder, and we insert a solid bar or powder, I'll get to that, a solid bar, and at the bottom, that pin is our feedstock material that we're adding to the application. So again, you see the example here. Now we're making a rectangular platform, but now through RPMs and linear forces, we're able to heat that material via friction forces up to about 80% of its solidus point, and then we begin to print the metal. So we don't melt it. That's the key to our technology. We don't melt it, and therefore it's a solid-state technology. And with that, we're able to configure it with a solid bar or a powder. Now we highly recommend the solid bar because it's a lower cost raw material, readily available off the shelf from various sites like Take Mattress, for instance. You can find that 3/8 of an inch square solid bar readily off the shelf. But again, we can add powder hoppers to our machines. We're not picky. It can be fine or coarse, from nano to a couple of millimeters in sphere volume. And we're able to process both solid bar and powder. But again, the solid bar, because it's less expensive, less handling issues, less storage life issues with respect to the powder. But again, it's a multi-feed process, either solid bar or powder. The whole process is based similarly to friction stir welding. The process restructures the grain size and order of magnitude. So on the left here is our 3/8 inch square bar feedstock of aluminum 2139. Has an average grain size of about 400 microns. After we deposit the material, the average grain size reduces to around 10 microns. So from 400 to 10 microns, more than an order of magnitude reduction in grain size. And all those metallurgists and technical fellows love grain size technology and so forth. So we really reduce that, and from a linear to a equiax position and strength. So we have a strength in all three directions, similar to what's been established for friction stir welding over the last 2 decades. But it's the same with the MELD process, because again we're using the same type of friction forces in the forms of torque and linear force. Whoop, 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 whoop. Sometimes throw in sound effects. All right, so what do? We have a wide range of applications. I have some slides on each of these, but here's just a real quick overview. We can manufacture near-net shaped parts. A large demand for our repair side because of the ability to repair unweldable materials with examples. Coating has been a home run with regards to rate of mass loss. Secondary process, we can print onto existing structures or components. And again, joining as noted with the friction stir welding capabilities of our equipment. Now to get a visual on some mechanical properties. One of the things we claim is you can choose any metal type, and I might repeat this like a Southern Baptist pastor a few times as I add the series of benefits, but choose any metal type. We can use any aluminum metal type. So on the left, I've got a cast aluminum, a couple of powder bed aluminums, and our mechanical properties of AL775. And I just want to point out, we're not comparing apples to apples. 775 should be a much stronger material, but again, you've got the flexibility of using any metal type and a visual to show really good mechanical properties. The next slide is very similar, the same cast, the same powder bed, ALSI10, and now you see that same 7075 as deposited and after our heat treat. So again, in many cases, our as deposited mechanical properties meet the mechanical properties without a need for a heat treat. And if we want to bump it up, we can use what we have our own custom blends of heat treatments to improve the mechanical properties. So again, a quick overview, you choose your metal, and here's a comparison of other technologies to say that as deposited or with a heat treat. It's got really good mechanical properties. I hope to expand on that in a little bit. And so far, aluminum is the only material that we've heat treated. The rest of the materials, mechanical properties are well above the threshold without the need for a heat treat protocol. And I'll show that with Inconel 625 coming up. Again, choose your own metal, any metal type. This is just a snapshot of some of the metals we've worked with. You know, friction stir welding started off with aluminum. And so we started off with aluminum. So we've got a lot of data on the complete families of aluminum, including a NAB, nickel, aluminum, bronze for like a Navy propeller shaft or propeller, magnesium, copper. We've done work with titanium, steel, nickel, a number of NMC composites, which I have one slide on that coming up. So again, it's any metal type. Fast deposition rate. I mentioned 30 pounds an hour. Here's just a visual on deposition rates of other technologies. I put my sources on the left-hand side, so I'm pretty reasonably accurate with all my data. Residual stress. Well, we're solid state. You shouldn't expect there to be a lot of residual stress, so I picked out a horrific powder bed example, so it doesn't really count. But I look over here at a technology that has a high deposition rate. It's a wire melt-based technology, and there's a 3/4 of an inch plate, a good amount of material, and just some of the challenges you have with a melt-based AM technology. In comparison, here's a 3/4 of an inch plate. If you did the volume calculation, about, I'm rounding up to 3 times the volume compared to this example with no signs of residual stress. And in fact, we did a project a couple of years ago where we incrementally reduced the plate thickness to see when we would observe residual stress, and we got down to, where's my mouse, a 0.08 of an inch, a very thin plate, finally showing signs of residual stress with a little uptick on the outside part of the plate. Again, don't want to oversell this. We're a solid state technology. We don't melt the material you should expect, low residual stress, but there's some visual verification of that. I'm going to get into some applications. I mentioned, make sure I didn't skip one. Okay. I'm going to go through a couple of repair applications because we found surprisingly large demand for this, especially in repairing cast and forge, replacing cast and forge applications and repairing cast and forging molds and so forth. But here's an example to hit home on the technology in terms of addressing unfriendly materials. Here's a cast magnesium helicopter transmission gearbox. That rib is prone to failure. At the moment it cracks, it becomes an $80,000 piece of scrap material because magnesium is unweldable. But it's not unmeldable. We use the same cast AZ91 magnesium. We machined down the rest of that rib. We deposited a number of layers, that's a 1/2 inch track here, a number of layers of the same material. So again, any metal, or we can use the original indigenous material for repair. So there's no politics about a substitute material. If it's magnesium, we use the same magnesium. And that was a home run. We demonstrated the ability to repair that magnesium-based application. Another example had a two-hit challenge. Another unfriendly material for repair, 775, but the location. I call it the location from hell because the underneath of that bracket wears over time in flight vibration. So there's this 7-foot long missile rail launch, just a series of long brackets. You're sliding the missile into that rail. It's on the jet fighter, and again with vibration. Over time, it begins to wear out the underneath of the bracket. So how in the world did we solve that problem? MELD has a couple of amazing miracle benefits, and I'm sorry I'm hyping that up a little bit. But we placed the MELD tool on top of that. It's about a 1/2 inch gap right here, or a 1/2 inch thick bracket. We put the MELD tool on top, 3/8 inch solid bar, 775 aluminum, and we began to push material. Where's my mouse? Push material from the top, extrude it through the bracket. We push out the worn material below the machine line, machine it back, And voila, home run for MELD. We demonstrated the ability to repair unfriendly aluminum, but a location that was very difficult to get. And I just want to emphasize that that's about a ½ an inch, and we pushed material through, because I'm going to show another example in repairing a Navy nav propeller where there's lots of pits in it that are significantly less in depth. And I'll reference that when I get to that slide. Here's an example with the Army where we demonstrated the ability to repair combat vehicles. They're mostly aluminum 2024. We were given a plate with a series of simulations of armor-piercing holes and a variety of cracks. We deposited fully dense material. Okay, there's my next one. Any metal type, indigenous material, now fully dense. And that's a weasel word because it means many things to many people. Our definition is no porosity, no voids. There's no need for a post-tip or vacuum furnace, and that's what fully dense means to us. We get better than rot mechanical properties, which I'm going to show coming up. And the main purpose was to demonstrate the ability to repair combat vehicles in the battlefield, and we passed this first round of tests. We've gone into a SERDIP project where they're actually taking the battlefield scrap and shredding it into little chips, little scrap pieces. You can see it's not very attractive. Again, we said any powder type. We're not picky from coarse to fine, and that certainly meets the definition of a coarse material. And we demonstrated the ability to print that recycled material. So putting that all together, we're looking at now with the Army setting up setting up a machine to place a large robotic arm on a transport vehicle, attach our MELD head to it, repair combat vehicles in the battlefield. And for instance, if this tank had a large section missing, we could print a near net shape part and meld it into place, at the closest MRO to the battlefield. So that's kind of a visual about where we're heading with some of our purpose-built machines. That machine would also have the ability to add hybrid tooling or subtractive manufacturing. I think in the battlefield, no one's going to worry about how pretty it is. It's just that we melded it with the same 2024 aluminum. I'm going to get into some coating. I just do a family of repairs, many more, but I'm time limited. So here's an example of coating. And what I see here, we start off with the traditional cold spray, thermal spray, and MELD, all using Inconel 625. I've got a series of about 5 slides coming up on a project that hits all the highlights of the MELD process benefits. So I look at cold spray and thermal spray, and you see the traditional challenges with the technology in terms of voids and porosity and so forth. And depending on the surface area of the application, a reasonably long time to prepare that surface before the coating. By comparison, we do no surface prep. We immediately meld the material onto the application. We get a fully dense bonding because at that interface, we plasticize both materials. In this case, you're going to find out this is the Inconel and this is a HY80 steel. So we're joining dissimilar metals and we're plasticizing them both at the interface, creating a strong metallurgical bond. And now I'm going to walk through that application to point out all the capabilities of MELD. So we got engaged with a Navy submarine propeller shaft made out of HY80. It's coated with Inconel 625 for wear resistance. So I'll start off with, we had a sample that was corroded. You just saw this on the other slide. We immediately deposited with no preparation, fully dense, which to us means no voids or no porosity. We have eliminated any pathway for corrosion to work, and any way for porosity. Any pathway for corrosion to work back to the surface. So I'm emphasizing here how we handle corrosion by, in this coating application, no vehicle or no pathway for the corrosion to work back to the surface. Here's a snapshot of the mechanical properties. Here's the prevailing technology, slag surfacing. Our mechanical properties exceptionally exceeded the requirement. Don't want to oversell that. That's the spec. So unfortunately, all I can say is we exceeded the mechanical property requirement. Of course, we passed the bend test in terms of no delamination or cracking. Again, we get a strong metallurgical bond. So you now begin to see the interface layer between the Inconel coating and the HY80 submarine propeller shaft. You see layer to layer. But the whole purpose of coating is to get a lower rate of mass loss. That's the whole purpose of a wear resistance. And so there's the standardized test. We took a 1-inch cube of HY80 steel. We melted a couple of millimeters of Inconel 625. This is the wear test, and the results were pretty impressive. We set a new value for rate of mass loss. Fatigue, up to 4 times the number of cycles to failure compared to the feedstock material. Really good fatigue data. Here's our Inconel as deposited compared to cast and wrought and other additive manufacturing technologies, and you see a significant comparison of our yield strength and ultimate tensile strength compared to a cross-section of other technologies. Let's see if I have one more slide on that. Oh, sorry. So I want to kind of hit that. Any metal type. Well, Inconel 625 was chosen as a coating application, fully dense, no porosity, no voids, no HIP, no vacuum furnace. Fully dense means there, from a corrosion perspective, no pathway for corrosion to work back to the surface. You saw very large improvements in mechanical properties compared to the prevailing technology. You saw fatigue data. You saw our technology compared to multiple applications here on this slide. And that kind of summarizes our technology in one application in terms of the benefits up to the fact I didn't mention the deposition rate. Again, and I showed that earlier that we're past deposition technology. Another coating application, a gun rail joining copper to refractory metals. Again, we passed the bend test and so forth, but I want to point out here in the slide the shear stress results. There's copper on copper, copper on tantalite, tantalite and copper on niobate. The shear stress test specimens show the fracture occurred away from where we joined the dissimilar metals. You'd think where we joined dissimilar metals, the copper to the 2 refractory materials, that may be our weakest point of the test specimen. As you can see, it fractured away. So again, we have good microhardness data, which I've got coming up, and really good mechanical property data. And now I'm showing, in this particular case, the strength of the joining process, the joining the dissimilar metals or copper to copper, again, fracturing away from where we join the materials. Here's a repair application for the Navy. It's a NAB propeller. We were given a section. We don't have a machine that'll support that yet. A section of the propeller, heavily pitted. You can see some orange in here, corrosion. We came in, no surface prep. We began to meld 1/2-inch tracks of NAB. We set a new value for microhardness. There's that NAB material flowing across that NAB propeller. Now, we're not doing the side here. We're doing the top surface. And the one thing I want to point out, well, if I could do it. One thing I want to point out is I'll play the video again. Well, if I can play it. All right. I showed that 1/2-inch thick bracket, extruding material through the bracket and pushing out warm material. I'm just suggesting that at the level of these pits, we are melding that material completely into those pockets and cavities. In fact, the Navy wanted us to machine the propeller, print, and then machine it back to spec, and we said we prefer to give it a try, just machining or printing and machining and save a step, because we're going to fill up those cavities and voids, and that's where we're at with that program with the Navy. Well, then we got so in coating and repairs, another application is components. Here's a aluminum 6061 pressure vessel dome. It's got a 2-inch diameter hollow insert, about 1 millimeter layers. Near net machining, that's just a handful of mills to machine it to near net shape. And I'm always looking for something sexy about our technology because we're fast deposition. I mentioned aluminum up to 30 pounds an hour. We don't get a lot of complex applications, but in this case, we were able to demonstrate a 54-degree overhang, totally enclosed the top of the dome with no supports. Here's an example of copper on a rocket nozzle. Here's an example of magnesium where we printed some Army Picatinny rails for the assault rifles. Here, now we're getting into printing onto existing structures or components. So here's the Orion crew module window frame. We printed features onto that frame. This is after machining. And each of these Z heights are at different levels. As part of that window frame, you can see it attached here on the module. So again, now we're printing or we're melding material into an existing structure. This is the home run that put us on the map with NASA. They wanted to reduce their airframe thickness, obviously for less weight, better fuel consumption. They needed to add ribs for reinforcement, and we got involved with NASA a couple of years ago, and of course we were crowing, oh yeah, we can use the same AL2139 aluminum, and thought we had it nailed, and the NASA funded the project and sent us some airframe panels. Then they said, we have to have a phone call. So we get on the phone and they say, congratulations. And I say, congratulations for what? Because we used the same 2139 material? They go, no, that's a bonus. We wanted to let you know that the whole intent of this project was to evaluate the mechanical properties at the intersection of the ribs. We've done this with other additive manufacturing technologies that melt their feedstock. You're the first technology to pass this test with no mechanical property issues at that rib intersection. We found a technology that would allow us to print ribs onto this airframe. And of course, we've been singing Kumbaya ever since because NASA has turned into be a valuable partner. They adopted friction stir welding 2 decades ago, back in 1991, and put friction stir welding on the map. And we're seeing the same type of relationship with NASA, and we're hoping they put us on the map big time like they did friction stir welding. Now I'm going to, again, we're going to print onto an existing structure. This is an automotive application. This is the rail of a large transport truck, and that's the cross member. So there's 2 rails and a cross member, and you can see it's a thin bracket and a thin rail. And the client was having a lot of stress issues at the interface there between the rail and the cross member. Makes sense. Thin rail, thin bracket. What we did was we took a section of the rail. Here it is. Now we melded a good amount of material. We're going to attach it to both rails through that bolt opening just like it is on the bracket. But now what we've done is we've eliminated 2 brackets, 16 bolts, which is always interesting. But the main reason is we solved the stress issues here. We weren't permitted to show that slide, but you see the prior original configuration, and now with MELD, again, we just added a bunch of material, joined it to the rail through that same opening here. And we also addressed some corrosion jacking, again, because we deposit fully dense material. There's no ability for that corrosion to work its way into and through the surface. See if I can get to the next slide. We've done work with titanium. You can see MELD as deposited compared to the ATI data sheet. So again, as deposited, we were showing really good mechanical properties as deposited compared to the data sheet. We've done we haven't done a lot of titanium work over the last few years. We've done a handful of projects. We've currently achieved a deposition rate of 5.5 pounds per hour. The more we play with the material, the faster the deposition rate as we optimize the parameter settings on our machines for titanium. You know, it's kind of hard. We work with every metal and we can't master them all at once. I look at the Arcam machine, and they promoted titanium for 2 decades before they went into nickel alloys and other materials. So here we're addressing all materials in parallel, and we just haven't mastered them all. Again, we started with aluminum, magnesium, copper, the softer materials, and I've got more to say about that later on, but here's a project on titanium as a joining technology. Okay, again, based on the principles of friction stir welding, but now our pin is not solid connected to the tool. It's our feedstock material coming out the bottom of the tool. And so we get 100% tool wear, which is a joke because we are melding that pin or our feedstock material as the material to join the plates. And here's a couple of things we can do differently. You can have plate height mismatches. You don't have to have same height plates. You know, we can add different height mismatches. We can put a gap in between the plates to do a thicker weld. So here's an example of 2 aluminum 2024 substrate plates. There's the plate. I'm sorry, that's not the plate. Sorry, that's the end of the plate. That's in the plate. So we have a gap here. We had a gap for a thicker weld. Of course, we passed the bend test. No delamination or cracking. After we completed the process, via optical or an etched image, you see no signs of the joining. So again, what's important here is that we can also serve the same capabilities as friction stir welding, but now with plate height mismatches or a gap for thicker welds. Getting close. Oh. Again, as a joining, we can join dissimilar metals. Here's aluminum and copper. Here's aluminum foam melded to a support structure. Here's joining some steel plates, which is interesting because with a friction stir welder, excuse me, I take a 5-second break. Sorry, I had to take a sip. All right, so we're showing the ability to join or meld those steel plates where the friction stir welding tool gets a lot of wear on the pin, and our pin is the feedstock material. MMC work. Well, we can add powder hoppers, do MMC work. If you're just hell-bent on using powders, you can use powders, but we typically recommend our mill machines for MMC work. We have a client who says it takes them 6 months to get data on their MMC experiments via a CAS process. And when he gets notification that the data has arrived, he's like, oh, that was 6 months ago. I'm way past that. I forgot about it. I'm not interested. Here we go. Well, we can print that in a day, and as fast as you can test it, you can have your data in a week or 2 weeks if you don't have the ability to expedite. You can see your MMC data in days instead of months. So here's an example down here in the bottom of copper with about a 30% tantalum. That white is the tantalum. So you see a good homogeneous mixture of the two materials. Here's aluminum with molybdenum. Again, the white being the molybdenum. So another good homogeneous distribution of the two materials. Then aluminum with tungsten. I think what really sets us home in terms of MMC development is we did a project where we took some aluminum and we added with 10, 20, and 30% increments of silicon carbon as a reinforcement material. And the data shows, as you would expect, the stronger or the higher percent increase in the reinforcement material, the better the mechanical properties. So with your MMC development, you're able to find out the right best fit combination for the parameters you want to hit in terms of the base material and the ability, the mixture you would like to make with that particular MMC composite. Make sure it's good. All right, so what do we offer? We have a commercially available model called the B8. It's an R&D machine. It's got a print volume of 36 by 12 by 12 inches. For some additive manufacturing technologies, that's a good size build volume. For us, it's small. We're a CNC type gantry-based machine. Our technology is scalable. No one's going to buy a 10-foot by 12-foot gantry-based system to print ribs on an airframe without going through their AB allowables and their application development and that systematic series of data before you say, oh, I got enough data to build this part for a production environment. So we designed the B8. This is our 4th generation machine. It's not like we just came out with a machine. 4th generation, designed to our specs, manufactured by MELD, and we target, R&D facilities, universities, and institutional research facilities because they have their cluster of industry members, just like America Makes. And those industry members are able to reserve blocks of time on the machine, develop their application and or series of test specimens for mechanical properties. You know, after you go through that phase of collecting all your data, then we talk to you about a specialized or purpose-built machine that can be multi-axis, can have hybrid subtractive capabilities. You know, I showed you an example of a robotic arm onto a transport vessel to repair combat vehicles in the battlefield. We're also in discussions with a couple of OEMs with respect to airframe panels and printing ribs onto those panels with a gantry platform of 10 feet by 12 feet. And again, so it's just a matter of evolving the technology. Again, we're focusing on two parameters, torque and linear force. We don't have a wide variety of variables that impact the print. So we get consistent print we get consistent results from print to print and from machine to machine because, again, we're using a stable material, which is a solid bar. We're not melting it, so we don't have a lot of challenges with mechanical properties that have a tendency to freak out being a melt base. It's a CNC native G-code programmable application. You know, this machine will be in our portfolio for decades. It's an R&D machine. There's nothing that's going to come out in the next 10 years in terms of torque and linear forces that's going to be a game changer for our technology because it's based on, you know, friction stir welding and based on a CNC-based gantry application. And that is the amazing MELD presentation. And we end with our slogan, "Don't melt, MELD," my contact information. And we're going to go into the question phase. And there were a couple of questions that were provided ahead of time. And then we'll, of course, be happy to get to your questions as well. And the first question is, does MELD need a gas flow chamber or tent to print titanium and nickel alloys? Good point. Yeah, I didn't mention that when I showed the titanium work with ATI. Part of that project is we were determining whether we needed a tent or we could do an open atmosphere. And so we printed the titanium, open atmosphere, no tent, obviously no gas flow chamber. And ATI measured the build plate and measured the print, and they only found minor differences in the nitrogen and oxygen content, indicating that we can print titanium, nickel alloys, and other sensitive materials without the need for a tent. Obviously, that means without the need for a gas flow chamber. And so we can now claim that MELD technology can expand its gantry-based platform to support these applications or these materials without the need for a tent. Okay, what's the next one? What metals? Okay. I mentioned earlier our primary materials that we have the most experience with, we would call them mature, is the across-the-board aluminum family from the 1000 to the 7000 series, copper and magnesium. We're aggressively working on steel. We have a lot of steel applications. We'll probably look to master that material next and then follow it with nickel and titanium as, you know, adding to our portfolio as a maturely developed material. Part of that involves adding, upgrading or developing new MELD tool materials to address these stronger metals. So we're in the process of tooling some new tool materials to address these materials. And so with that, we'll certainly jump right onto a number of our top steel projects and start collecting more data. But with regards to aluminum, on one of our machines for 2 years, 0 tool wear to date of processing aluminum. What type of tool wear?
Jay, we have a few questions that have come in now.
Go ahead.
Insert them. Sorry, I somehow hit the wrong button and hung up on you when you were about to go into the question mode. So
you hung up on me.
Yeah, sorry about that. Didn't affect anyone else though, so you handled it well. So we'll jump into these. So the first question that came in is around the precision of MELD, and specifically the question reads, or is questioning, what is the minimum wall thickness that the process can yield?
That is a great question. Okay, now today we use the off-the-shelf 3/8 inch square feedstock. And with that material, we're able to get track width from a 1/2 inch out to a little over 2 inches. In our roadmap, we go to I call it the mini meld, don't have a name for it yet, but it's going to use a smaller, a smaller square feedstock in terms, probably down to a 1/16 of an inch, maybe a little smaller in the wire range. Of course, that's a new machine. We got to increase the RPMs by a factor of 10 and reduce the linear forces by a factor of 10 so we don't buckle the material. Well, that'll give us much smaller track width. And on the other side of that, when the demand's there, we'll go up to a 1/2 inch square feedstock, and that essentially doubles our deposition rate from, I use aluminum as an example, from 30 pounds an hour to 60 pounds an hour. Don't want to claim that. It's just conceptually, mathematically, it doubles the deposition rate, and of course the track lengths will be wider. So that's it. Now when we do parallel tracks, the inside of those tracks are fully melded together. You do a CT scan or some type of analysis, and you won't be able to detect where the two tracks join together. On the outside, like in friction stir welding, we get a couple of mils gap between the plate and the material, and that's to be machined off. There's a couple mils of machining, and I think I answered that question. Go ahead.
Yep. Yeah, I think there's another question that I think you've kind of addressed already, but I'll ask anyways in case you have anything to add that is related. So the question is, how do you create small features on a large block? Is it through use of a small feed tool or post-meld machine the feature? So I don't know if you want to expand any on just dealing with adding small features to a substrate or something that, you start with a block.
Sure. Another great question, and I partially answered that as we, in our technology roadmap, as we've designed it, but we haven't started building it because of other projects in front of it. But what I call the mini meld, where we use, for lack of we don't want to give away the recipe, but I'm going to use a 1/16 of an inch square compared to the 3/8 inch square, 1/16 of an inch square, and that's going to sizably reduce our track width to do finer features. And then on the other side, today with our 3/8 inch square, if you need it smaller than a 1/2 inch track, you're just going to have to machine it today until we can offer both capabilities on the same machine. So that's my answer to that. Future, smaller track width with the smaller feedstock material. Today, it's machine it back if you need to be, 3, 4, 5 mils total thickness.
Got it. Perfect. So I have two two questions that are pretty closely tied together, so I'll ask them at the same time, both related to applications.
All right.
So the lead-in is, are there any meld machines currently in production? And then more general, and related to that is, what are the applications that they're working on, if you can talk about it, and more generally, what are the main, target sectors for this technology?
All right, great 1-2 punch question. Yeah, the MELD model B8. We've been selling that for 2 years. We have them at less than a dozen universities and research facilities, and of course we're growing our business through the machine sales of that particular unit. I use the University of Alabama as the example, and we don't name all the sites that we've got machines at, but University of Alabama's got a number of papers published, so it's public domain. And their industry members in this case include Boeing, Lockheed Martin, NASA, and a group within the Army Research Lab down in Huntsville, Alabama. And we've been working with these beta customers for a number of years. Then we worked with them directly through the University of Alabama. And these are the type of customers that are much further down the learning curve. And so We transition them from the prototype or the R&D machine to a purpose-built machine. But this is the only one we've announced that's commercially available right here. So that kind of addresses it. We are selling the machines. We also do R&D services work here at our facility to help, explain and promote the technology. And then, of course, the industry members. It's a great benefit for MELD as a small business because now that university holds, a dozen industry members' hands and does all our work for us, developing technology, writing some awesome papers. Sometimes a graduate paper can be, I'm making this up. I used a MELD machine and the application sucked. But thankfully every paper's been amazing. We've just been so happy with the papers. We see these graduate students being hired with a preference at NASA, Boeing, and Lockheed Martin to transition technology into from academia to the OEM. So that's kind of my overview on the university settings and so forth. And we do sell the machines. And what was the other question? I'm sure there was a two-punch. I think I missed out on the second one.
Yeah, it was kind of generally speaking, what are the target sectors or kind of what do you envision as application space?
Yeah. This is the most fun we have. When we have our own little webinar, and we got a group of engineers within the same company, and we say, you have to just basically eliminate everything you've learned about additive manufacturing in terms of complex applications, because we don't do complex applications because of our deposition rate. It's a near net print process. So then we began to say, well, what do you guys do? And so we found a lot of applications for repair, which I hit on, a few for coating. We get into casting, aluminum casting. There's all sorts of industry backlogs, and we have one OEM that's actively qualifying our process as a I don't want to say substitute, as a replacement for aluminum casting. They've identified 20 to 25 applications that are in their pipeline with long lead times, and these are great applications for the MELD process. So, over the year, you'll see us announce that if the OEM allows us to acknowledge that we've qualified the MELD process to replace some casting and forging applications. We really just get with the group of engineers and we have a brainstorming session. They begin to talk about applications. They go, that's a good fit. That's not a good fit. Here's why. And after about 30 minutes, we come up with about 4 or 5 really win-win applications and the ball gets rolling. So again, AM printing as a cast or forge replacement, specifically aluminum is being qualified right now. Repair, we can repair all day long. I can't really go into the specific applications because of NDAs, but there's just a wide range of applications. That's why I hit them generically, from printing components to repair to coating to friction stir welding examples and joining. Sorry. So it's just a wide range, and it really takes some time. I would prefer or recommend that with any big individual that's listening in, if you want to schedule a telecom, and we'll include our AM manager, Dr. Cox, and we'll sit there and we'll go through the types of problems you're having or type of applications, and after we nail a few and say that's a bad one, this is a good one, here's why, then they just start flowing. And that's the best way to describe it, because I can't reveal a bunch of them because, we got to respect the application with respect to our NDAs. Yep.
Yeah, no, makes good sense. Good thought starters. You'd mentioned a couple of times in your most recent answer friction stir welding and the relationship or kind of similarities to the MELD process. In terms of qualification, if friction stir welding is qualified, as it is in some applications that we're aware of for aeronautical purposes, railway, otherwise,
right?
Is MELD technology then directly accepted, or have you found that full process qualification is requested? So, root of the question: if friction stir welding has been, or friction stir joining technology is acceptable to an application space, have you had any scenarios where you've been able to use the approved qualification process and introduce MELD instead?
Great. Thanks for saying MELD. And the answer is no, but let me back up on that a little bit. The process is the same. We get the same results with respect to the reduction in grain size and the equiax nature of the process. You saw a MELD Inconel as deposited mechanical properties, and one of those technologies was friction stir welding to show that we're the same or better in that one slide. We've not had anyone approach us to go through the qualification. I doubt anyone wants to take any AM metal technology, solid state or others, and just rubber stamp it based on a few pieces of data. So I believe that we'll have to go through the qualification process before there's enough industry data to bypass that process. And that leads me into AM repairs. We've been doing these repairs for a while, but now we're set up to do a host of Navy AM repair applications where we're going to get qualified by a third party. In this case, we formed a relationship with Penn State, who's, if you're familiar with them, the Office of Navy Research has about 6 man-tech centers. Out of those 6 man-tech centers, which includes Penn State, they have only one rep tech, which means repair technology. It's only at Penn State, and they have an IMAS group, which is NAVC, NAVAIR, NAVSUB, MARCOM, and SPAWARS as voting members, and Penn State, ARL as the non-voting member. And they've been doing qualification for cold spray AM repair applications for quite a while. And now we have programs in 2019 and 2020 where we're actually going through the qualification process for applications that are funded to get our first qualification approval in our Navy code. Yay, I can't wait to announce that, but that's where we're starting there, and I imagine it'll come to fruition. We're working with some customers. I mentioned NASA on some slides that does a lot of friction stir welding. I believe their intent this year is to qualify the MELD process as a potential replacement for friction stir welding. In fact, maybe actually print the entire application. But again, NASA's calling the shots. We're in early stage process to qualify that application, but we're not qualified, but they're a logical partner based on their 2 decades of experience with friction stir welding.
Awesome. Few more good ones coming in here. So this is about operating conditions or parameters on the system. So in particular, on the B8, which is available. How critical are the operating parameters of the B8 machine in controlling the quality of deposition? Are these parameters set by material and fixed, or is there some opportunity to try different formulas or loadings, torques, etc., to try to yield different results? Great question.
And the answer is kind of yes across the board, but let me see if I can peel that onion back a little bit. I'm going to use aluminum as the example, basically because we've hit the 1000 through the 7000 series, some unique blends, and I mentioned NAB, nickel, aluminum, bronze. And so we can work with you to do initial test specimen. You come back and say we like areas for improvement in these areas in order to hit our sweet spot. We can do parameter optimization. It's really not that difficult. It's torque and linear force combination. So we could do a series of tracks at different torque and linear combinations. Again, now we're starting to close in on the best fit parameters for the specific material that you want. We've done this, but we can't provide that data. It belongs to the domain of the company under NDA. But, for the guys that want to try it out for the first time, we can do a series of tracks with different combinations of the 2 parameters we vary, which is torque and linear force. And then we can take it from there as deposited. And we can develop and optimize a heat treat for aluminum. Our heat treat doesn't respond to the industry standard. It requires its own unique recipe. I would say we've got a handful of R&D type formulas. Some balance out yield strength, tensile strength, and elongation. Others bump up yield strength and ultimate tensile strength at the head of elongation, and then one is I'm getting off track. So just a family of heat treat protocols that we would develop together because we just can't provide those open source given the fact that these were developed with our partners. So yeah, a lot of ways to spin this to zero in and do material development and then print it onto an application and move it from there.
And related to your very last comment there, or the last couple parts of your comment, related to degradation of elongation. So question is the degradation and elongation related to finer microstructure from the MELD, the MELD material, if you will? And is there a way to improve elongation? So are there, can you talk to that degradation and just either things you guys are working on or maybe areas of opportunity to look into moving forward?
All right. So I'm going to use aerospace as an example. In most applications, the critical spec or the spec you're supposed to meet is the yield strength. So we ensure that we meet the yield strength spec. Rarely do we see elongation specified as a critical component. But the answer is yes. If we work together to develop a optimized heat treat, which you'll see improvements in elongation, and I'd prefer to take the rest of that offline and have a one-on-one with that particular partner that's on the call today because we don't want to give out too much information without getting certain clients under NDA.
Perfect.
Well, I'm sorry, go ahead.
No, I was just going to say, I think that's the last of the questions that came in externally. I don't know if there's other things in the last couple of minutes you want to cover in the balance of questions you haven't got to. Yeah,
real quick. I'll whip them out real quick. Do we see any mechanical property differences between printing a solid or a powder? Nope. For the same material, under the same conditions, we see no differentiation in mechanical properties. Again, we're melding that material within 80% of its solid at this point and printing it, and so we're not seeing any differences in mechanical properties comparing apples to apples between a powder and a solid. I touched on the different tracks of today, 1/2 inch to 2 inches, and I talked about the future with what I call the mini mill or a smaller solid bar down to a 1/16 of an inch. It would make finer details. I've mentioned so far with aluminum, we've doubled the deposition rate to 60 pounds. Again, just call that a comment. We haven't verified that mathematically. It does that. Do metals require heat treat? Aluminum so far today is the only material. All the others as a positive have met the mechanical properties, so we haven't been challenged to do any heat treats on anything other than aluminum. I mentioned about our AM repair technology for defense. As we move into 2019 and 2020, a number of repair applications behind our belt, but none that were specifically set up for qualification qualification, the process for the application and get a Navy code. One thing I want to point out is at NAMT, where the Navy is going to build 10, the goal is to build 10 Navy restore facilities. They prioritize AM solid state technologies. They specifically called out cold spray and additive friction stir. And then I got to tell them that additive friction stir is a MELD process. So, we're seeing a lot of rollout in the defense for repair, focusing on the cold spray and the MELD process, which is previously branded as additive friction stir. What about the next one?
I got one last question that's related to that just came in that I think is interesting. What is the required distance from the MELD print head to the base material when doing repairs? How is this distance maintained on a repair with non-planar surface?
All right. So I can't give out the specific length, but I can tell you that with our solid bar feed mechanism, it's slowly based on our parameter settings, we're slowly pushing it out at a certain rate below the tool And I'm going to have to leave it at that until we talk to that client under NDA.
Awesome. No, I understood. Thanks for telling us what you could about it. I think, unless you have really critical points on that last question, I think we're kind of at our time right now, and would like to thank you for your time. I mean, really interesting briefing, and for everyone's awareness, this all was captured and is going to be made available on our YouTube channel here shortly, so it'll be available that you can pass along to others as necessary. And Jay's contact information, just for reference, was listed at the very beginning of the slide presentation, so you can reach out to him directly if you have further follow-up and questions. And I'd like to close by just thanking you, Jay. I really appreciate your time and pulling this together and bringing everyone up to speed on the technology.
Amen. If I have a 30-second close, that is, while I'm speaking for 30 seconds, I'm asking the guest to determine what is the 10th letter of the alphabet, and I'll come back to that. I want to say thank you for the opportunity to present MELD technology today. Obviously can't cover everything in a presentation, so we'd love to take it offline. We are making this data available through the America Makes YouTube channel, but just ask that you share that information inside your company. Don't publish it in a public domain forum. It's still considered sensitive material for us, but want to make it available to the industry members with America Makes. And getting back to the answer to the 10th letter of the alphabet, it's the letter J. And that's my corny way of saying my name's Jay, and I appreciate your time today, and hope to chat with you in the future. Thanks for your time today.
All right, thanks, Jay. Appreciate it.
All right, bye-bye, everybody.